Hello, this is solving a circuit using algebraic topology. Really, this is meant to be an intro. Let's move my microphone up. This is meant to be more of an intro to homology, algebraic topology. You really do not need algebraic topology to solve this problem. It's a very simple problem. But I want to introduce homology because for a variety of reasons. And you do not need homology to solve this problem. But if you were writing a circuit solver in a computer, that might need homology. So there is a utility for homology. And homology is just really cool, and it generalizes a lot. But let's just get started by explaining the problem. So we have this circuit diagram here. These mean batteries. So there's two batteries. One of them is 12 volts, one of them is 5 volts. The longer terminal means the positive node. These three are resistors. This is a 4 ohm resistor, a 3 ohm resistor, and a 2 ohm resistor. And what we're meant to do is solve for the current going through each resistor. I'm just going to briefly make sure I'm actually still recording. Am I recording? It seems like I'm recording. Okay. Okay, so the rules, there's depending on how you count them, I counted 3, maybe more. There's Ohm's law, which relates, so we're given something in volts and something in ohms here, and we're trying to solve for current, so this is how we relate them. So voltage equals current times resistance. Another way of saying that is that it doesn't matter. That the unit volt is equal to the unit amp times the unit ohm. Okay. Voltage drop over any resistor. Oh, that's right, we're solving for voltage drops. So voltage is, its unit is joules per coulomb, and so it's kind of potential energy. It's potential energy per unit charge. Well, potential energy, the phrase potential energy is meaningless. You have to talk about the potential energy between 2 points. So really voltage, the correct way to think about it is voltage drop. So what is the voltage drop as I go over a resistor? Well, the voltage drop as I go from over a resistor is the current going through the resistor, and current obviously has a sign now, is the current going through the resistor times the resistance. Okay, and if you're a physics person, I'm sorry, I know I butchered that, but this is as far as I understand it. I want to talk about topology, that's why we're here. Alright, and then the loop rule, this is the one where topology is going to help us, is the sum of voltage drops over any loop is 0. So if we go back up here, oh, and I forgot, we need a sign convention, which is that the voltage drops when going from plus to minus, so you can think of plus dropping to minus. So voltage drops when going from plus to minus on the battery, and we assume that wires have no resistance, therefore they have no voltage drop because of Ohm's law. Junction rule, this is the last rule, and then I redrew the circuit down here in a much more colorful way, which is that the current entering a junction is equal to the current leaving a junction. So let's just look at the circuit really quick. So train your eyes, just look at the yellow. The yellow is just the same diagram as above, and I redrew it in a little bit more careful way. We have two batteries, one's 12 volts, one's 5 volts, the three resistors in the same configuration. Okay, train your eyes on the blue. I drew arbitrary directions for the current going through each of these resistors. If the direction is wrong, we will simply get a minus sign for the amount of current, so the directions are completely arbitrary. And then down here we have a junction. Well, we have 3 currents going in and no current going out, so I1 plus I2 plus I3 equals 0 just by the junction rule. So next, train your eyes on the purple, or violet, that's right. I had a mnemonic. Cyan is for current, C current. Violet is for voltage. So by Ohm's law, the voltage going through here is equal to 3I3 in volts. Or correction, the voltage drop along here is 3I3 in volts, and we should probably, that's going into the negative terminal of the battery, we should expect that to be a negative voltage. We should expect that this is the wrong direction, and then we should get a minus sign in front of I3. Doesn't matter. Alright, the voltage drop when going from the positive to negative terminal of the battery is 12 volts. There's no voltage drop along the wires, because they're wires, and we live in a fantasy world where wires don't have any resistance. Picked an arbitrary direction for the current, so the voltage drop along this is 4 times I1, that's the resistance times the current. And then voltage drop along this resistor is 2I2, so 2 ohms times however this many amps, and then 5 voltage drop across the battery. Okay, so if you've solved a few of these problems before, you can probably solve this almost in your head. You write down the equations for these two loops and the equation for the junction rule. You get a system of linear equations. That's a 3 by 3 matrix. So you get, AX equals B. Therefore, X is equal to A inverse B. And there you're done. You solve it. However, that relied on you visually detecting that there are two loops here. If you're writing, say, a circuit solver doesn't have eyes. It can't just look at this and see that there's two loops. And maybe in a really complicated graph, the number of loops isn't super clear. There is a way to count them using the Euler characteristic, but I'm not going to get into that. You still have to find out what the loops are in a very systematic way. And homology is a very good systematic way of doing that. But anyway, you have 3 unknowns, so you need 3 equations. I don't know if I mentioned that. You need to use the junction and loop rules to produce 3 independent linear equations. I just explained how to do that. So the junction rule says I1 plus I2 plus I3 equals 0 because they're all entering one node with no current leaving that node. And then you go around this loop, so 12 plus 3I3 minus 4I1 plus 0. That's got to be equal to 0 by the loop rule. Same over here, 4I1 minus 2I2 minus 5 plus 0 equals 0. I wrote down those equations later, so that's why I'm speeding through them. Alright, so eventually you'll get, I said this, a 3 by 3 invertible matrix A. You need an invertible matrix. A times I1 times I2, I1, I2, I3 equals B, and so therefore I1, I2, I3 equals A inverse B. So homology will actually give us a very systematic way to get this matrix A, and guarantee that it's invertible, kind of. So I wrote this down. Homology clearly, and there's no way you can read that. Homology clearly and systematically gives algebraic descriptions of the independent loops. Now, what do I mean by independent loops? I will get to that in a quick second. Actually, I will explain homology and then explain what independent loops are, and therefore that'll really dig into why homology is actually pretty important here. So this graph, I just took the graph for the circuit and took out all the junk about, and we're just looking fundamentally at the shape. I drew these edge directions arbitrarily. They may or may not match the edge directions in the original matrix. It doesn't matter, because all we're going to do is figure out how many holes there are in this graph. Now, it's obvious there's 2 holes. But, well, not quite, because you can go, here's a hole, here's a hole, and here's a hole. So, well, no, we just counted 3 holes. That's interesting. So we have to define precisely what we mean by a hole, and then we have to come up with a way of counting them. Well, homology answers both of those questions. So what you do is, for each of these edges, so E1, let me zoom in so you can see, E1, E2, E3, E4, E5, E6, E7, what you do is you define the boundary of an edge to just be the, again, these are formal integer linear combinations, but so the boundary of E1 is sort of the vector notation for E1. So the boundary of E1 is V6 minus V1, so it's tip minus tail. And it doesn't mean anything beyond V6 minus V1. Likewise, boundary of E2 is V5 minus V6, boundary of E3 is V4 minus V5, and so on. And I wrote down a table here. Boundary of E1 is that, boundary of E2 is that. It doesn't really matter, you can check my work. All that matters is that we wrote down what the boundary of each edge is. And then what we do is we define this boundary map to be a linear map. We just say it is. So in particular what that means is now boundaries operate on chains. So the boundary of E1 plus E2, well, that's now, because it's linear, the boundary of E1 plus the boundary of E2. Well, boundary of E1 is V6 minus V1, boundary of E2 is V5 minus V6, so the boundary of E1 plus E2 is the boundary of E1 plus the boundary of E2. Well, we get a plus v6 here and a minus v6 here. So that's a very long-winded way of saying that if we enter a node the same number of times we leave it along some sort of path, then that node cancels out. Well, loops have the property that they always enter a node the same number of times that they leave the node. So, for instance, we take this loop here that goes around. Well, it picks up a v1 from e6, loses a v1 from e1, picks up a v6, loses a v6, picks up a v5, loses a v5, picks up a v2, loses a v2, and so the boundary terms will all cancel out. And so, in algebraic topology fantasy world, you define loops to be things where their boundary map, you assume the boundary map is linear. Loops are defined to be integer linear combinations of edges such that their boundary is 0. So for instance, I just went over this e1 plus e2 plus e6 plus e7. That is a loop. That is a loop. You take its boundary map, boundary of e1 plus e2 plus e6 plus e7. Well, by the linearity, you can just take the boundary of each of those and add them up. So boundary of e1, that's v6 minus v1, plus boundary of e2, that's v5 minus v6. Boundary of e6, that's v1 minus v2. Boundary of e7 is v2 minus v5. And you notice, color palette. My brush is too big. I'm gonna cancel these out. Well, this v6 cancels with that v6, so plus v6 minus v6. Minus v1 cancels with plus v1. Plus v5 cancels with minus v5. Minus v2 cancels with plus v2, and we get 0 at the end of this. Okay, well, we have a system of linear equations, and we're trying to find what inputs to that system of linear equations imply that every single equation is 0. If that doesn't quite make sense. So I butchered saying that, but what I mean is we take this system of linear equations and we write it as a matrix. So the columns correspond to edges, and so we put in a column vector of whatever weights on the edges. So for instance, what's meant to go here is that if you have something times e1 plus something else times e2 plus something else times e3, you put those coefficients in the column vector in order of e1, e2, e3, e4, e5, whatever. You get the point. So e1, so if you're just talking about e1, you put a 1 here and zeros everywhere else. If you put just talking about e2, you put it. It should be noted, and this is a notational mistake by me. Let me. I don't have the drawing pad, so this is going to be bad. All right. That this column is 7 items tall, and this matrix is only 6 items tall because there's 6 vertices and 7 edges. So really, this column vector is 1 longer than the matrix. That was my mistake. Okay, so I didn't feel like writing out anything here. But anyway, what we want is, what input do I put into this column vector such that every equation comes out 0? This is a very classic linear algebra problem. This is called finding the null space of this matrix. All right, and so I wrote a program that is very good at calculating the null spaces of matrices. So let me just quickly go over what this matrix is. So E1, so this column will contain the boundary of E1, and I don't know if you can see these little gray things down at the bottom. I wrote those mostly for myself. So the boundary of E1 is V6 minus V1. So in V6 you put a 1, V1 you put a minus 1. And so that if you put the column corresponding to just the argument E1 in here, you would get a column corresponding to V6 minus V1, if that makes sense. So you put in a column vector here, you get out a column vector. So the column vector here is 7 items tall. Column vector here will be 6 items tall, and it'll correspond to, you put in some arbitrary chain here, you get out its boundary. So that's what it's meant by the boundary is a linear map. And you just add up the boundaries using this way. If there were coefficients, you're only allowed to put integer coefficients here, and I'm not going to explain why. It's because this isn't a vector space. It's a Z module, or it's some algebra nonsense. Anyway, if you had like 2e1 here, you would put a 2 here, and that would mean that the boundary is 2 times this boundary, which would be 2v6 minus 2v1. Again, it's a lot of algebraic formalism, but it's really clean, and that's important, and it's very systematic. Again, I got distracted. So v6 minus v1, that's a boundary of e1. Boundary of e2 is v5 minus v6. Boundary of e3 is v4 minus v5, and so on. And so it's just the boundary of this edge. You put a 1 for the plus sign, a minus 1 for whatever's on the minus sign, and you fill out this matrix. And what we want to do is we want to find loops. Well, loops are defined to be chains such that when you take the boundary, all of the boundary terms cancel out. So we put a chain in here, or whatever column vector corresponds to a chain, and we want to know what chains will end up with all zeros when we do this matrix multiplication. Okay, and so the way you do that, you calculate the row-reduced echelon form of this matrix, and the reason is that the row-reduced echelon form has the property that its null space, so if you have a matrix X, the row-reduced echelon form of X has the same null space as X. That's the important property. And so this row-reduced echelon form also has the property that it's very, if you know how, and I'll maybe link a video about how to do this, if you know how, you can look at this row-reduced echelon form of the matrix, and then just read off what the null space is. And I'll explain how to do that in a minute, but I want to show you the program I wrote that calculates this. So this is a library I've been, oops, I didn't mean to show you that yet. Here we go. This is a library I wrote called QAnal. It stands for Rational Analysis, and the reason is because it's a very long story, but I don't like the way that computers have been. Yeah, it doesn't matter. Anyway, so here we can, this is a very simple Erlang script that lives, I'll put a link to this in the description. QQ, that's the library I wrote. QM means rational matrix, so Q stands for quotient. So this line just says compile this before trying to run it, and then that way you don't get weird things with the dependencies of functions. Main defines a matrix M, which is equal to QQQM of this string. In Erlang, if you just put two strings next to each other, it concatenates them. I wrote a string parser that converts this internally into a matrix representation that's useful. Then we take the row-reduced echelon form of M, so QQ rational matrix, RREF row-reduced echelon form of M. Then OK, PP, that stands for pretty print, the reduced row echelon form. And when we do that, this is the matrix that pops out, and as you can see, I copy and pasted the same matrix into here. Alright. So, we can just read off what the null space is. So, suppose we have a 1 for E6. Okay. What this means is that, I'm not going to be able to get into that, but if we take one of this column, 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 and one of this column, well, if you look at the rows, they will all cancel out. Okay, so this vector, this is meant to be a column vector, but I put a transpose symbol there. 1, 1, 1, 1, 1, 1, 1, 0, that's in the null space. And then this other vector, just again using the same trick, we look at where the 1s are here, scan over, put down a 1, 1, 1, but now we have minus 1's here. 1, 1, 1, 0, minus 1, transpose. I will put a link to how to read off the entries of this matrix, or what the null space is given the reduced row echelon form. It's pretty easy, you just kind of have to have some practice with it. But these correspond to chains, and so what this is saying is that these are a basis for the null space. Now what does that mean? What that means is that not only are these two loops, but every sum, every linear combination, so you take x of this plus y of that, where x and y are integers, those will always be a loop, and any loop will be an integer linear combination. So these two vectors contain all of the loops, as long as you allow for some, weighted sums of the two. But let's just look at what these correspond to. So this is E1 plus E2 plus E3 plus E4 plus E5 plus E6, no E7. That's this big path. E1 plus E2 plus E3 plus E4 plus E5 plus E6. So we just do this random linear algebra calculation. Somehow it corresponds to the loops in this matrix. It's kind of amazing. Or loops in this graph. Well, 0, 0, 1, 1, 1. Okay, so that is E3 plus E4 plus E5 minus E7. That's this right. E3 plus E4 plus E5 minus E7. Those are the two loops. Well, how do we get this left loop here? So E1 plus E2, no coordinate for E3, plus E7 plus E6. We take this first loop, which was the big loop, and subtract off the small loop. Look, that would give us 1, 1, 0's here, 1, and then this minus 1 becomes a 1 because we're subtracting, which gives us E1 plus E2 plus E6 plus E7, which is this loop over here. So right away, the way to think about this is that the space of loops is two-dimensional. And these are the sort of unit vectors, or rather, the space of loops is two-dimensional in this graph. And so we have two independent vectors in that space. And so what that means is if you put a third vector in, well, it has to be on the same plane of these two vectors. So if you think about a two-dimensional space, you put two vectors that aren't collinear in the space. If you put a third vector in, it has to be in that plane spanned by the original two vectors. Any two independent vectors will span the plane. You put a third vector in, it must be a linear combination of the first two, just by geometry. Right, so what this means is that if we use that loop rule, well, so our loop space is two-dimensional, we can only derive two independent equations. But if you remember, we had three variables. That's why you need the junction rule. So we look at this again, and I kind of drew a simplified form. So this 12 means the voltage drop over the battery. This 5 is the voltage drop over the battery. These 2I2s, 4I1, 3I3, those are the voltage drops over the resistors. No voltage drop over the wires. So if we look back, and I'm going to show you this, let's take this left loop. So 12 plus 3I3, no component for I2, minus 4I1 plus 0 is equal to 0. I just wrote that as an equation here. The right loop, plus 4I1 minus 2I2, no component for I3, minus 5 is equal to 0. Just that's the loop rule, which is the sum of voltage drops over any loop is 0. The big loop, so we miss I1, but we pick up 3I3 minus 2I2, 12, and minus 5. That gives us 7. So we get three equations here, but we know the loop space is two-dimensional now. And look, when we just add the left and right loops, these 4's cancel out to give us 0. 0 minus 2, that gives minus 2. 3, 0, that gives 3. 12 minus 5, that gives 7. Now, what does all of that mean? What that means is that if you try to use the loop rule to derive three equations, you can't. You're only going to get two independent equations. Now, if you know a little bit about linear algebra, you know that if I try to make a matrix out of these first three linear equations, it's not going to be invertible. And because if you have a row in a matrix that is a linear combination of the other rows, then the matrix isn't invertible. So that's why you need this junction rule, which comes from, there's three, didn't mean to show you that. There's three currents entering this vertex and no current leaving it, so I1 plus I2 plus I3 is equal to 0. Alright, so what I'm going to do is I'm going to take the left, the right, and the junction rule and put those into a matrix. So we get minus 4, 0, 3, and then move the constant terms over. So minus 4, 0, 3 times dot with this vector, that's going to equal to 12. 4 minus 2, 0, dot this vector is going to equal to 5. That's just, these two are this first two are the loop rule, and then this one is the junction rule. 1, 1, and 1 equals 0. Okay, well, hopefully this matrix is invertible. And what we conclude from that is I1, I2, I3 is equal to the inverse of this matrix times this vector, right? We just multiply on the left by the inverse of this matrix to both sides of the equation. Oh, I didn't mean to put 3 equal signs there. Oh well. What was I saying? Oh, and when we do that, it gets 3 halves, 1 half, minus 2. Inverting this matrix by hand maybe is a bit of a pain, but you can do it. I wrote a program. This is part of the QNL library. So, again, we have main. This says A is equal to QQQM, rational matrix. It's the same matrix from before. 4 minus 4, 0, 3, 4 minus 2, 0, 1, 1, 1. B is equal to this column vector. The semicolon means drop to a new line. So minus 12, 5, 0. A inverse is equal to the left inverse. If the matrix is invertible, its left and right inverses are the same, but because of the way it's programmed, I make you pick whether you want the left or right inverse. A is equal to the left inverse, or AN is equal to the left inverse of A. The result is equal to X means multiply A inverse times B, and then pretty print the result. Circuit 2.Earl, and it's equal to 3 halves, 1 half, and minus 2. And if you can look here, there we go. That's what I wrote here, 3 halves, 1 half, and minus 2. And I will leave you to check that if you substitute 3 halves, 1 half, and minus 2 into here, that it obeys both the junction rule and the loop rule. I didn't check that, so it's possible I made a mistake, in which case you get to find my mistake and leave a mean comment. So there's some motivation for you to check, because I didn't check. Alright, that's all that I want to talk about with homology. I think that is reasonably clear. Please let me know what changes I should make, or rather, what isn't clear, and I can go over it in a different video. Alright, thank you for watching.